Hello, thank you for having us at CCGrid 2021. My co-author David Bernbach and I are at the Mobile Cloud Computing Research Group at TU Berlin and Einstein Center Digital Future. In Edge of the Earth Replication, excuse the wordplay, we look at web content delivery in large LEO satellite communication networks. You might not have heard of the LEO Edge before, so let me give a short introduction. There are a number of private companies out there that are currently building large satellite mega constellations in low Earth orbit, or LEO, which are used as communication networks. So low Earth orbit means altitudes of less than 2,000 kilometers. And these constellations comprise tens of thousands of satellites. And they are used as high bandwidth, low latency internet uplinks. So wherever fiber access is not available, say in rural areas, on planes, or cargo ships, small satellite dishes can be installed that connect to these constellations. We refer to these small satellite dishes as ground stations, through which clients access the network. And even if fiber access is available, satellite internet could still be a better option. That's because satellites have inter-satellite laser links between them. So the constellation provides a global network of point-to-point routes. If two ground stations on opposite sides of the Earth can both access that satellite network, communication between them can even be faster than via terrestrial networks, thanks to faster light propagation in the vacuum of space. Now, this animation shows the initial phase 1 plan for SpaceX's Starlink constellation, which is probably the most well-known LEO mega constellation. The animation is sped up by a factor of 8, but you can easily see how fast these satellites move in relation to Earth. This constellation has 24 planes of 66 satellites each. You can see that a group of satellites always follows the same orbit, and we refer to this as a plane, the orbital plane. Imagine a circular plane cutting through the Earth, and the satellite orbits follow that perimeter. Now, you can see that this global point-to-point network is drastically different than the hierarchical tiers of the internet that we have now. Instead of traversing tiers through routers and across the AS nets, all global clients and servers share one wide area satellite network now. And that is a challenge for content delivery networks. So currently CDN providers put their points of presence within tier 3 networks where the clients are. And additional POPs can be placed in tier 2 and tier 1 networks for tiered replication. But in the global satellite network, how can CDN operators place their POPs now? Well, we have drawn up a number of options. First, obvious, no POPs at all. So all clients simply fetch their desired web content from the origin location. We don't worry about any data replication. That's simple to implement and doesn't require any storage within the network. And given the high bandwidth, low latency connections, the customer impact may even be negligible. But it does, of course, it does put a high strain on the network and origin server. As a second option, let's imagine fitting ground stations with storage. We can replicate our web content directly to consumers who can access that content without tapping into the satellite network at all. And the cost per ground station hardware is relatively low. Think compute power of a Raspberry Pi maybe, and some storage hardware. But does that scale? With every household potentially having their own ground station, that's quite a lot of points of presence to manage. And this doesn't yet consider how one would even manage equipment in the hands of customers. So our next logical option then are satellite POPs. Satellites are where the paths of different ground stations to a web server converge. So one replicated data item can be served to many customers if they request the same item. That saves on storage hardware, and the replicated content is still available close to the consumers. However, satellite hardware is slightly more expensive, and the biggest challenge, satellites are mobile. So you see ground stations constantly reconnect to that nearest satellite for optimal network connectivity. In the constellation 1 I showed you, such a reconnect happens about every 90 seconds. Additionally, the Earth also rotates underneath the constellation, as you can see in picture 3. So ground stations also move between orbital planes. If we store data replicas in a satellite, those replicas will quickly go out of reach of the ground station. But we can easily predict when those handoffs happen. So what if we add a time to live to our data and simply purge the satellite cache when ground stations reconnect? So when the satellite leaves the area where its data is relevant, it no longer stores any data and can serve a different geographical region. Of course, once that TTL expires, we must first fetch all requested data again from the origin locations. And the other challenge is that once the satellite has completed its orbit, it may be in the original location again and could make use of the original data. So constantly fetching data from the origin location can be a deal breaker because it puts strain on the satellite network. So what if we instead make use of the inter-satellite links that we have? So remember, it's expected now that each satellite has a connection to its successor and predecessor in its own orbital plane and its neighbors in the neighboring planes. So since we can easily calculate when handovers happen, we can just move our replicated data in the opposite direction of satellite movement. That leads to a virtually stationary replica stores. So from the ground station's perspective, it looks as though the needed replicas are always in the same nearby location. Of course, constantly moving those replica stores also puts strain on the inter-satellite links. So we have these 5 different options for POP placement. How do we find out which one is likely to be the most efficient? Well, we did a simulation, and these are all parameters, just short overview. We're using the Starlink constellation that I've already shown and a CDN workload based on real-world CDN traces. And we're doing 2 sets of simulation with 2 different country data sets, the USA and Switzerland. Both are different in size, so that just gives us an idea how distribution of ground stations influences results. We are also considering different ground station densities. So does a single satellite dish serve 10 or 100 or even 10,000 clients at a time? That's currently still an unknown. And you can, of course, find the detailed simulation description in our paper. So we use a custom-built simulation tool that you can find on GitHub as open source, and we also have that link in our paper. Now, for the sake of brevity, I will only share results with the US dataset with you now. Again, the other dataset is, of course, in our paper. And we're looking at 2 metrics. The first one are hops per request over time. So we can't really check bandwidth or latency, since those depend on constant factors that are still unknown at the moment, given that satellite constellations are still under construction, and there's only a few measurements have been done so far. And we are also not considering hops from devices to the ground station, but only hops within the satellite network. So that again is a constant factor of 1 hop or 2 hops, depending on the implementation of the network. So in this graphic, you can see a few things. Let's look at the dashed dark line at the bottom first. You see that requests with the GST POP placement strategy are served from the ground station store. Hence, there are no hops within the satellite network at all. And we see that after a short amount of time, almost all of the requests are served from that local replica store. On the other hand, on the top of the graph, you see that the continuous dark line where no CDN POPs are active. So each request must make the complete path to the origin server, which is about 15 hops on average per request. You can also see the spikes in constant intervals below that. This is where the TTL expires and content is fetched from the origin server again. So we see that on average, that's 50 hops. And after a short period of time, after a few seconds, most of the most of the data, of the requests are served from the satellite POPs. So for the SAT and SAT replication strategy, you can see that the average hops are about 1 each time. So the single hops from ground station to satellite, and that satellite has a replica of the requested data item. Let's look at the average required storage for each POP in the different strategies. We haven't set a storage limit for POP because that would require us to also set a cache replacement strategy. And we don't really want to evaluate cache storage sizing here or different replacement strategies. We instead want to find out what order of unique items actually come through or through our POPs. So obviously, our first strategy without any POPs is absent from this graph, since it doesn't require any storage at all. For our GST strategies, we can see that the broader distributions of client leads to less average storage needs, as each ground station serves less unique items. Think about the normal CDN item popularity generally follows kind of a Pareto distribution where 20% of the items make up 80% of requests. For the SAT strategy, the number is even lower as ground stations share a single satellite. And in this SAT rep strategy, we have the advantage that a great number of satellites do not share any data, since they are all over areas without any ground stations. And so there's no data in that virtual location. And the SAT-TTL strategy looks even better, since all data that was only accessed once, maybe at the beginning of the simulation, early in the day, and not again after that. So one data item of the 80% of data items that is only less frequently accessed is not replicated at all. And you can also clearly see how the local store is cleared every about 90 seconds. So let's come to a quick conclusion here. We have shown that CN operators need to rethink POP placement with satellite-backed internet on the rise, since the old strategy of placing POPs in Tier 3 networks will not work anymore. And we've also investigated 5 different options for POP placement in these large LEO satellite constellations. And it turns out that placing POPs on satellite is not only an option at all, but also a very effective one. That is, if replica stores are frequently cleared, for example, through a cache replacement algorithm or on a limited sized store. And we see that predictive replication over inter-satellite links can further increase efficiency. That also opens up a few further research questions. So how do our findings change with different satellite constellations? What kind of cache replacement strategies make sense here? And how will we size a satellite store for effective cache usage, replica placement? And how would a prototype of such a CN look like? How would we even evaluate that without access to a real satellite network and real satellite servers, which is another issue? So those are just a few insights from the paper. I encourage you to read the complete paper and learn a bit about LEO satellite constellations. And well, thank you again for your attention, and we're excited to hear your thoughts via email.